to class 8. Ooh, we need to change that. This is class 8. All right, so we fixed that. And we're dealing with chapter 14 and gear stress. So now we're going to deal with non-AGMA wear. So we're going to go back to some topics that we covered in ME470, and that is contact stress. And if you'll recall, one of the things that we dealt with contact stress was the one of the scenarios where having two cylinders that were in contact with each other, and when they were pressing down against each other, they form just a line until you start pressing them more with more force, and then they're going to deform and form a rectangular kind of section in there. And based on someone's calculations, I didn't do the derivation of this, but we can take a quick look at that equation 373 and pick it apart, and we could see that you were able to figure out what 1/2 of the width of that rectangle would be, this thing called B, right? This measurement of B. And it's a function of the force that you're placing onto the thing, the length of these cylinders, so that L right in there. And and by the way, these people, they might be using 2L, but we're just using L. I just noticed that for the first time. That's just wherever I got this figure from. I thought it was a good figure, so I used it. So you'll see what the equations we have are just for L right in there. So somebody else's equations will have something else in there. And then we see how we have Poisson's ratio, and that's for each of the materials. We also see we have the elastic Young's modulus, the elastic modulus for each of the two materials. So that's in case you have gears made out of different materials, and sometimes you do. And then you have the 1 over the diameter of each, right? So that's what that function is that we find that piece in there. So and you can see that these equations are in chapter 3. That's where we covered that in ME470, but you also see that it's in chapter 14. So that's where it's being introduced here as equation 1410. Now we don't need to use these equations in this class, but we need to know where the stuff is coming from. What we see instead, what we can use in this particular chapter, is we have this thing that they call the elastic coefficient, and you can see the C, capital C subscript P right here. And if you take a look at that, you can see where this stuff has come from, right? You can see that we have this we have Poisson's ratio divided by Young's, 1 minus Poisson's ratio squared divided by Young's modulus. We have in both places. We have that right in here. We can also say we have the pi. That's right in there, okay? So, and we see that it's the square root of this right here, which is just like we have right there, the square root. So that's what we have right in here. We can see that we can take that when we go to implement this, right, for the equation that is in that's in chapter 14 for the non-AGMA surface durability. So you see right here, that's that section of the book right there. I don't think the page number is correct for the 11th edition. But we can also see here in this equation that they've provided right here. We can see the 1, we have this 1 over the radius plus 1 over the radius. So we can also see that that's like right in there. And then we can see we have the load that's being placed right here. Interestingly enough, and we can also see we have L right here, and that L is going to be, for us, is going to be a capital F, right? And that capital F represents the face width, right? So just going to try to keep track of where these numbers are coming from, where these variables are coming from, where these equations are coming from. And we also have a dynamic factor that got thrown in there, but that's like a modifier, right? It's just amplifying that what the load is, right? So they're taking the static load and they're making it into a dynamic load by multiplying it by this dynamic factor kV that we had previously discussed in the previous class. They also are adjusting for a little bit for the orientation of the force by dividing it by the cosine of the pressure angle, because the force is not just the perpendicular force it's not just the transmitted one, it's the magnitudes, because that's the one that's actually running across. If this is the tooth profile right here, the load that's causing contact stress is the one that's the total load that's being perpendicular to it. So that's what that's all for. And you can also see that the radius that we're going to use for this, you have to look down and see this other equation right here, that the radius that we want right here is actually the radius of curvature of the tooth itself, there's not any other radius. So you got to be careful. We're going to take the pitch diameter and multiply it by the sine of the pressure angle. And this is just a rough estimate, by the way, of the localized curvature of the gear tooth, right? So that gear tooth has, we know that it's going to be this involute shape, and so to make a rough estimate of what that is, right, the curvature localized of that right there, we're giving a radius. That's what we're saying that radius is right there, right? And it isn't necessarily, we don't actually have that curvature for sure, but this is an estimate of it. So you can see that, right? So it's a good idea to compare these two things and figure out where all of them are coming from, and also see where the sequence are. All right, so we want to use that, and we have to, okay, so that's stress right here, and we need to compare stress to strength. So we need to come up with a means of establishing, well, what is the strength? What's the contact strength? And also, this is going to be fatigue, right? So something we didn't cover, or I don't even think I brought. Sometimes I do bring it up or try to highlight it, but we didn't use it for anything. Is the surface fatigue strength that is in Chapter 6 right here? So if you go to section 616 of the book, and look this up, you'll see that there is some information here. First off, something that's true with that can be done with lots of different ultimate strengths or strength in general is you could find a relationship between the hardness number that you might have used in mechanics, material science, or I forget the name, what they call the class here, but it's in the lab where you take the Rockwell hardness number. There's also the Brinell hardness number. And if you recall this, they're taking a metal and you put it into an apparatus and you make a little dent into it, and it gives you a reading, and it kind of tells you what the, so you can have like a range of what the hardness of a material is. Well, that hardness is actually easily related to the ultimate strength. So we can actually find in Chapter 2 where they have that relationship, and we'll look at that again in. There's also another. They bring this up again in Chapter 14. So if we could find a relationship where it's proportional to, and then we subtract out a little bit, and we're able to get a strength right here. So here is a long-standing correlation between strength and hardness, but also in this case we have a particular strength, and that's going to be the contact strength that we would use, right? So this is the value that they were used. Now there's this section right here that's a little confusing, and so to avoid this confusion right here, we're just going to use the comparison of that contact strength and that fatigue contact strength compared to our contact stress right there. They're making the case that you could actually that maybe you want to use these as the square of them, because within the formula right here, right, we're taking the square root of this right here. So maybe if we want to try to find a better correlation. But for the most part, we just have, we just want to find this ratio and then try to assess it with this. So that's what we have for today. And let's do an example here. Let's do example, we'll go over example 14.3 in the book. So we have a pinion. This is the same one that we had for examples for 14.1 and 14.2. And they have now we're going to say that it's that's mated with a 50-tooth gear, and it's made out of ASTM number 50 cast iron, right? So the other one was made out of steel, and now this one is made out of cast iron. And using the tangential load of 382 pounds, right? Estimate the factor of safety of the drive based on the possibility of a surface fatigue failure. The surface endurance strength of the cast iron can be estimated to be 0.32 times the Brinell hardness number for 10 to the 8 cycles. What's 10 to the 8 cycles? Is that 100 million? Yeah, I think it'd be 100 million, right? 10 to the 7 would be 10 million, so this is, all right, so let's move on to here. Now, some things that we want to do is make sure that we're getting oriented with the book and finding things in the book. So let me grab a hold of my book right here. I'm going to use the 11th edition, even though I have a lot more of my numbers are going to be the 10th edition here. So let's see, one thing I should do is look up material properties, right? So you might not be able to find some material properties easily, so I'll try to help you with them. Some of the first ones that we're going to need right here are in table A5, right? So I didn't even realize, I think at one point that this table was in here, but it's a pretty decent collection, and they don't have a lot of choices, right? They just go a basic steel in here. They go carbon steel, and then they have cast iron, right? And so they don't have a lot of variation. So they just use 30 for 30 either 6 psi or 30 mega psi here for our Young's modulus. And you remember that sometimes you use 28.5 and sometimes 29. You'll see it can vary for steel, but they just, a common thing to use in many engineering books is just use 30. And you see a great cast iron significantly softer, or I'm going to say soft, more flexible, right? That's interesting right there. Also, you can notice that it's good to, actually I see 10 a lot of times, so I think maybe they might have changed from 10 to 10.4. But anyway, you can also see that they have Poisson's ratio listed down, and for carbon steel they go 0.292, and for cast iron we have 0.211. And I might have used something else. No, I used their numbers. We can also find cast iron for its strength if we wanted to, just to let you know. It's in table, I think it's like in the tables in the A20, and they might have changed some of these with this edition. I don't know. Decimal equivalents for wire, stochastic yield and ultimate. Here you go. Here's for 3. Here's for cast iron right there, right? So when they tell you a cast iron number right here, here's where you're going to get the tensile strength, and so the ultimate strength and tension, ultimate strength and compression. You can also get Brinell hardness, right? So this is probably what we're going to need right here. And which one did they say this was for? It's number 50. So we have 262 is the Brinell hardness number that they're going to give to us. So let's go back to some of our things here. And so information, we want the gear, we're going to need the gear diameter, right? So we had the number of gear teeth and divided by the pitch. The pitch, if you recall from this earlier example, was 8, right? And the number of gear teeth, there's 50 right here. So we're going to 6.25 inches in diameter is the gear. Things I needed to look up for the pinion, we're going to use the elastic modulus of 30 E6 psi. Poisson's ratio for the pinion is going to be 0.292 that we just looked up. The gear is going to have 14.5 e to the 6 psi, because it's going to be cast iron. The Poisson's ratio of the gear, 0.211, all things we just looked up. And by the way, is that true? I think this actually doesn't agree with one of the tables in the back of the book. I think in the table that I said it was at A24, it has a different elastic modulus. Let me double check that up here, because we're in the middle of a video and you can just cruise on by that. Let's see. Is that true? No, I think this is fine. I don't know why I wrote that down. I don't see where they... the modulus of... Oh, no, they do have the modulus of elasticity. Okay, so they have a modulus of elasticity, and they say the modulus, it varies in compression, corresponds closely to the upper range right here. But anyway, we were dealing with cast iron 50 right here. So you can see that they have, their range is actually 18.8 to 22.8. Interesting, right? That's his intention. Maybe it's in compression. I don't know. We're going to use the 14.5 because that's what they say to use in this example, I believe. But interesting thing. So anyway, we want to get this elastic coefficient, CP, and looking back at what the equation for it is from the previous section here, you can look it up. We say it's going to be 1 over pi times, so we go 1 minus Poisson's ratio squared over the elastic coefficient. And we're going to add to it 1 minus 0.211 squared over 30e to the 6 right here in 1/2, right? So what we end up with is like 1,817. Now this thing actually has units, and they're the crazy units of square root of psi right here. Okay, so one thing that you might want to do here though is to note that in chapter 14, if we go to, we actually have these worked out for a number of materials, right? See, I gotta find it. I think it says table 8, 14.8. So if we go to table 14.8 in the book, it's got to be before here. I know this is exciting watching me flip through pages, isn't it? There it is. Table 14.8 already does this for you, right? So if you have like a pinion material, and let's say that the pinion material is going to be steel, and we have cast iron right here, they end up coming up with 21 right here, right? So, but they're using a different elastic modulus. They're using a 22e to the 6 elastic modulus. On an exam, I say go to this table right here and just pick out what the steel, and you'll notice that we have steel versus steel, so we'll use this one a lot. But notice what they've used as part of this right here. They used the 30,000 and they used the 22. Not 30,000, 30 million. They use this here, and they use the 22 million. Whereas if you go to this example that we have, that is example 14.3, which we're covering right here, and I'm specifically walking through these examples to let you be aware that we have these issues as part of that right there. You'll see that they used the 14.5 here for the cast iron. Whereas the other there's things that are contradicting it, so just be aware. And then another thing that we're going to need as part of this is to take the pitch diameter, or find the curvature, right? So we want to take R1 is going to be dP times the sine of the pressure angle divided by 2. And looking back over at that other example, example 1, you'll see that we had a diameter of the pinion of 2. So we take the sine, and it's a 20-degree pressure angle, and we get 0.3420 inches. And remember, that's going to be that radius is trying to describe a radius that would be formed, like if you were to take a circle and try to figure out what the radius of curvature was of that surface right there. And then we also have the radius of the other two, but of course these two are going to be the same diameter. These are gear teeth of the same diameter, just to each other, but because they're going to be a little bit of a difference on the larger of the gear right here. So, well, did I say cap? I did use uppercase G. Sometimes I'll use lowercase g in this. All right. So here we have the 6.25. and the sine of 20. So we end up with 1.069 inches. And so now we can get the stress right here. And they put a negative in there because it's compression. I guess they just want to emphasize that. And that equation that we're using right in there, remember that we're using this equation right here. So referencing that right there, we'll take our CP, which we found to be 1817, or we could have just looked it up in the in that table, and it would have been, of course, it would have been slightly different, right? And then we have our KV. So from our previous example, look back at that, and we get 1.524. They told us to go ahead and use 382, which was from the previous example. So like it's a little easier, I think, maybe to go in this direction. We could also figure out what the horsepower rating would be based on this, and that's often something we'll do. So maybe we ought to look into see what the rating would be. The face width was 1.5, right? Not to be confused with the force, it's an F. And then we take the cosine of 20 degrees. And then so now we take 1 over the radius of the gear, of the pinion, 0.342, plus 1 over the 1.069. And we had, and the whole thing, we take the square root. And what we find for our contact stress is we get a negative 72,550 psi. Now we have to evaluate whether, is that a lot? Is that a little bit? I don't know. So we look up in the book for the Brunel hardness number, like for ASTM 50. And we find that we get 262, right? So we can get our SC. That's going to be the endurance, the contact endurance strength is just going to be 0.32 because we're told this right up here, right? And that's going to be times 262. Ends up with 83.84 KSI, right? This is PSI, that's KSI, make sure we're comparing here. So according to them, the safety factor that we're using, I mean, one means of finding it is to have that SC divided by sigma C and square it. And we don't care about the negative, by the way. I don't know why we had to put that negative in there. So we say that that's going to be the 83.84 divided by our 72.55 squared, and we get 1.34. Whereas if we did it the other way, where we just say this, which is the way that I'm suggesting we do it each time, because I don't know if there's any point to this, to doing it with the square of the thing. Because you'll see we get 1.16, right? So it just depends what our criteria is going to what our criteria is going to be. For most things, the criteria is going to be set, and they would tell us based on the square or based on the ratio. But I think it would be better just as we're making a judgment call on this, we would do it ourselves right here. So I'll wrap this one up and then make another video for another example. So it's 25 minutes.